mode. Well, our last speaker is Patricia McBride. She is a leader in experimental high-energy physics. She's at Fermilab outside of Chicago. But also she has been heavily involved in the CMS experiment at the Large Hadron Collider at CERN. She's going to talk about the perspective from high-energy physics.
Hi, so I'm going to talk a little bit about the perspective from particle physics, and there's actually a lot to say about international collaboration in particle physics. So I'm going to keep this talk relatively short, so there'll be time for questions. So I'm not going to, it's a very abbreviated history of particle physics and international collaboration. And I started this out by taking a recommendation from the recent P5 Prioritization Panel, looking at future projects for the US in particle physics. And they started out by saying, pursue the most important opportunities, and what they mean, science opportunities, wherever they are, and host unique world-class facilities that engage the global scientific community. And that really is how particle physics is thinking about its future. So just a little bit about the science drivers of the questions that are sort of facing particle physics right now. This is obviously changing with time as we have new discoveries and we learn more things. So we have the Higgs discovery from 2012, so now we're going to be using the Higgs as a tool for new discoveries. And that involves the Large Hadron Collider or perhaps future colliders, future big projects. Pursue the physics associated with the neutrino mass is actually understanding the properties of neutrino. It's a particle we've known about for a long time, but we don't know very much about it. And that involves also big projects, which I'll talk a little bit about at the end. Identify the new physics of dark matter. That's done at colliders. That's done in sort of space-based probes and also in deep underground facilities looking for direct detection. That I won't cover here, but sort of the deep underground ones are sort of, in some sense, still in a national scale or a regional scale where they're more competitive rather than collaborative globally. Understand cosmic acceleration, dark energy, and inflation, where we're in the borderline with astronomy. And then explore the unknown, where you try to make experiments where you're trying to make a leap into understanding what's out there. So one of the main tools of particle physics has been accelerators. This is an early version, it's an early aerial photograph of Fermilab, where this is 4 miles around. This is an accelerator that was built in the 70s. And so I'll just go back a little bit and give you a little bit of background of particle physics. I don't go back as far, I took a personal sort of view, and so we have a long history of international collaboration. The goals that we set in sort of understanding the physics have demanded bigger and bigger machines and with higher intensity. So always pushing the technology, always pushing how we can build these things and collaborate together. So if you look back into the 50s, most people were working in their local accelerator. You heard about that in the earlier talk. A lot of college campuses, a lot of institutions had synchrotrons, cyclotrons, and people worked there with their colleagues down the hall. And in the 50s, that was when people started talking about international collaboration in a big way, and that CERN was formed as a European collaboration to put together to build larger facilities, and that started around 1954. In the 60s, then it really was national facilities or regional facilities like CERN, and collaborations on the experiments were like 10 people. So you would have your institute and maybe where your student went. And there were accelerators in the US, but the big sort of regional one came together at Fermilab, started in about 1967, and the first experiment was in 1972. And when you look at it, this is a group of US and Russian collaborators. The Russians had a gas jet that the US thought would be great to put into the accelerator, and that was really the first proved experiment at Fermilab. And I started working there as a student in the early 80s, and there it was, in every experiment, there was almost every experiment was international, though I worked on an experiment with only 8 people. Well, now I work on an experiment with several thousand. So the field has changed a lot in the time. We had visitors from China at that time that came and worked with us. It was, you know, I grew up thinking physics was international. It's not a change for me. But in the 80s, the experiments really, a lot of experiments grew as colliders grew, and the SPP-S at CERN, where the W and Z were discovered, the Tevatron at Fermilab became a collider, and then there was the LEP collider at CERN at that time, and the collaborations were hundreds of scientists and international. But the machines themselves were sort of national or regional. They were provided by a facility and operated by the country where they were, or the region where they were. And at that time, also China and Japan had built world-class accelerator facilities, which attracted international collaborators. So you know, these facilities, all the experiments, or most of the experiments, were international. So this is for the top discovery, which is at Fermilab in the 1990s. There were 2 large experiments. They were built by international collaboration, sort of in the ALMA model, where Italy brought the calorimeter, Japan was involved in building it. We had collaborations with Brazil, and you can see the list of institutions that were you know, part of the collaborations in the 90s to participate in the top discovery. And each collaboration had about 450 scientists. So you can believe there was a governance, and there was a lot of, had to invent how you have a constitution, you would make decisions on the design principles of the experiment, and how you would publish a paper with 450 people. So this, looking in, you know, so the 2010s, and this is a sort of an example of from Fermilab's point of view, our international collaboration, where in the 90s, everyone came to Fermilab or sent their things to Fermilab. And now Fermilab actually sends things out as well. So it's become sort of bilateral in that we participate in telescopes in Chile, and we participate in the CMS experiment at CERN, and we participate in accelerator facilities around the world, and have, so the white things are where we send things. We are in dark matter experiments in Canada, and working with Japan, and CERN has a similar map, and I'll talk about CERN in a minute. But this is really becoming a real international lab, though our funding is very national based. So I work on the CMS experiment, and I've been involved in it for about a decade. We work at CERN. It's a big international collaboration. This is now 27 kilometers around in the CERN site. There are 4 experiments, but 2 big ones that were involved in the Higgs discovery. Each experiment has about 2,000, 3,000 scientists and engineers working on it. They took a long time to plan. The planning for this started, I think, when you know, probably in the 80s, but the really proposals were in the 90s, and people were really building on construction for well over a decade in pulling all these things together. You see a picture here of some small part of the CMS collaboration. This is actually not the detector, but it's a detailed photograph of the detector at full scale. But they're complicated devices. And I said they also work on the ALMA model, where people, each country sort of brings their contribution to the experiment. But when it comes, and the accelerator then was designed at CERN. It was a CERN project, but had US and Japan contributions to some of the elements there. So, but when it came to getting the Nobel Prize, of course, the theorists got the prize. And, but all these people, the 10,000 people, stand behind them and really pulled this together. And it's a case of a lot of goodwill, and not the agreements and the treaties can't really make up for all the sort of the power of sort of the students and postdocs who pull all this together. And here are the 2 heads of the experiments of the time of the Higgs announcement, and Fabiola is going to be the new director general at CERN, and this is Joan Candela is from UC Santa Barbara. who was head of CMS at that time. So the model of governance in these big collaborations where the experiments are sort of on the billion-dollar scale and the accelerator is quite a bit bigger than that when it was all said and done and installed. It's a giant superconducting ring. It was technically challenging, really difficult to design and build and put together. And it's just coming back up after a 2-year shutdown, so in the next couple of weeks we'll be back online again. But let me say a little bit about the governance. They have in some sense, it's split between this host lab model where they manage the infrastructure, which the accelerator, the civil construction, in some sense the computing, other things, the networking, things that pull it together. And that's sort of managed by this formal treaty. It's run by the CERN Council. It's a very formal organization behind that. And then the scientific collaboration is much more by the ALMA model, which is very flexible, but has a definite order to it that has to sustain a collaboration of people working on a billion-dollar project from 1995 up through 2035. And that's something we didn't necessarily go to school to learn how to do, but we had to learn. We had to teach ourselves. It's not always perfect. When we have to make a big decision about a technology, it can, be a little bit of international ordeal and lots of phone calls and video conferences. But in the end, it works, and partly because people are very motivated by the science, and that drives it forward. So I just want to say a little bit about planning for particle physics priorities. We are really moving into this global scale, where it's not really going to be for some of the big projects where a region builds a facility and then people come to work there. It's really that the community, sort of global community, have to agree on what the next steps are. And still, our planning processes are very regional. That even in the Americas, we couldn't find an organization that actually where all the, Canada and the US and Mexico and Brazil talk together about it. We all talk as nations to each other and invite international partners to sit in on our discussions. But in the US, it's the High Energy Physics Advisory Panel, which advises Department of Energy Office of Science and the National Science Foundation, who provide essentially all the funding for particle physics. And they had a panel that met last year after a year of study, and it was almost a 2-year process in the end, came out with a very detailed roadmap for particle physics in the US, but with understanding that this had to fit into the global context. We had a lot of community input, a lot of back and forth, and it's a plan that has really a consensus of the community behind it, which has happened before, but we've been known for not always being on the same page, and I think this group really pulled the community and came out with those science drivers I showed you in the front, which everyone agrees on. So in Asia, it's national strategic planning. They do have a body where they get together and discuss about future accelerators, but that's not so much a planning body. In CERN, in Europe, it's really CERN together with the European Committee on Future Accelerators that puts together a European strategic plan. They are now doing that in more of a global context. The US sits in as an observer on that process. And then there's a global discussion forum, which is called ICFA, which is the International Committee on Future Accelerators. That started in '76. It was acknowledged that we were going to be looking at big projects in the future and that we needed a place to get together. It again, and talk about it. It again is not setting a priority, but it allows discussions between the directors of all the world laboratories to come together regularly. And it's part of IUPAP. So I wanted to use an example of something that's facing us sort of in the near term is how to take the next step in neutrino physics. And we are proposing to build a sort of global facility in the US for taking the next big step in understanding neutrinos. So this would involve a deep underground, large caverns in South Dakota. It takes from Fermilab and then sends a beam, which is neutrinos that go deep underground about 800 miles to this facility. And this was initially proposed about a decade ago and as a national facility. And it became clear as we understand how much it would cost and to build the cavern, build the improvements to the accelerator, and then build a detector underground. It was beyond the capability or the sort of budget of one country, and that it really needed to be an international project. And so in some sense, we're hitting a reset on this project to bring in the international community and allow them to be part of the planning process. Where a lot of international projects have stumbled is when a host country says, I have this great idea, why don't you send me money? And that doesn't work. So in some sense, this is we think it's the first time that the US will really host a large-scale science facility that is really global from the start, where we're bringing people in to work on the governance, work on the design, make sure it's not just us asking for, we take the credit and people come and participate. So as I think has been said several times before, we're really in this era where for big projects, one country and one region can't really afford it. And we need to, one country can't control the design, and we really have to understand how to come together and make global collaborations. And we've been doing this in the past, and we're trying to apply these models to this neutrino program. And it's inspired in some sense by the CERN model, but it doesn't have the treaty behind it, so it's going to have, for the facility, which is the accelerator and the cavern, and the utilities for the cavern will be sort of governed under these bilateral agreements between countries. And that's really being worked on as we speak. And these discussions of governance really are important, that we're not final in the design. So that's a really important point that I think we've learned from experience. And sort of our objective, or what we're grappling with, is how we can be a good host country for this world-leading long baseline experiment. And what do we need to do to be a good host and to be a good partner? And in some sense throw that out to you, because I'd like to hear some of your ideas. We talk about it, and also we'll come back with some of the challenges in the last slide. So I think this has been said before, but these science programs, you really have to balance the needs of, the national needs with the needs of the global science, of the science objectives, of how to maintain national expertise, how to maintain innovation and creativity on the local level. Over 20 years, you really still need to have scientists working and as individuals in these projects. So the governance is key. I'd say the scientific collaborations for us are working well. They're not perfect all the time, but they're working well. And then we've had a lot of experience in how to govern between countries. You still have to work with the funding agencies. You have to get everyone on board with decisions. It's not always easy. We have constitutions, but they're organic documents in some sense. But governance of a facility is more of a challenge. We have to worry about operating costs and other, in working with multiple governments and multiple agencies, and these multi-year timescales is our challenge. And the different cultures and what people expect from project management or accounting. You run into just roadblocks there about what your expectation of what a technical review is, or they're a challenge. CERN has been an example of how to break through in this, and we try to learn from that experience and in planning facilities for the future. And so for the neutrino program, that's sort of where we're starting and trying to adapt it to the current situation. And that would be true for any future collider program that would come up in the future. So I leave you with some issues for discussion. So the time scales are an issue, and it takes a long time for things to go from an idea to a construction to an operating facility to the first science paper. And how do we build these successful projects with the constraints of our annual budget process. That's something we grapple with. And then balancing national interests with enabling successful global collaboration. And there are visa issues about who's allowed to come visit and where are we allowed to go visit. Intellectual property issues, export controls, computer security. We build computer systems that go across the globe. We send our data everywhere. This makes some people anxious. I remember when I first heard a talk at Fermilab, somebody from Washington came to Fermilab and talked about the World Wide Web, which was something that was, came from the international collaboration in particle physics. They're trying to communicate with each other. And somebody came up and gave us a speech about how this was a problem, because you couldn't control what was being talked about or what was being sent back and forth. But these are issues that face us, all the time in trying to put these things together. And if you get bogged down too much in here, you never get the science done. So the scientists try to sort of ignore it and hope for the best. And if there is another project coming along in the particle physics community, sort of in the global, in the global scheme of things, how do you decide which one to join, and what if there are competing proposals? And this is something we may have to face in the future. So I leave you with that, and hand back the microphone.